Great. Ladies and gentlemen, thank you for the opportunity of being here. Thank you for your attention. The topic now will be a little bit different and apart from topics before, not just about high speed. It's the question, slab track is not just used for high speed, it's also used on these places in the world where a lot of trains are passing since decades. And the bad side of it is on these old structures, tunnels and places, you have to do some renewal. And if you have to change then the ballasted track to a slab track, it's like a surgery on the open heart. You're in the middle of the town and you have to do something and you are not allowed to risk that the trains cannot run the next day. I would like to share now the experience, our history, how we approach to it, giving some examples, some projects which we already did and others which are under investigation and development. And I just would like to invite you to understand how we lost our fear of applying these new solutions. What's the background? It's quite simple. The desire, you have an old track, you want to remove the ballast and put slab track in. Perfect, next. Unfortunately, it's not that simple and trivial. And there's one factor which people sometimes forget. It's not just the track and the structure itself, it's the subsoil. Because if you have an old structure, an old tunnel, an old situation, and the island is full of mud underneath the tracks, you have also to think, what do you do when you detect some problem underneath? What do you do if you have some renewal during the night shift hours and detect a problem? Yeah, you need a solution. The desired solution, and that's where we focused on, our principle is, if it's possible, to use a track also during the construction time, meaning you leave the track as it is and maybe some parts not finished, then you are much more flexible and the risk is reduced. I put the comparison at to the beginning. The traditional approach, and everyone knows it, is you have a track, you have some engineering hours, the last train is passing, and then people start there, run there, do their work. 20, 25 people on the same spot are trying to do whatever they can do, have no chance to really realign something, and they maybe can do some repair. And the situation is not special for UK or for Austria, it's everywhere the same. What can you do? How can you achieve a better performance? How can you achieve that you're more cost effective? Because of course slab track is, compared to ballast, the more expensive investment at the beginning, but then you have to do it that properly and that well that it has the better life cycle, the lower life cycle costs and achieves the expectations you want to. Also a big problem I want to mention, this is the material distribution. If you come to a site, it's almost impossible on an existing track to determine exactly what's the number and volume and weight of material to take out and to bring in again. You always need reserves. And all these reserves, as you make it very difficult. So, but how can you use this track, or how far can an existing track be used? And I want to start now, more than 15 years ago, it was in 2000. This is now from the slab track construction from Cologne, Frankfurt. And I remember when I started there, and we presented our adjustment system, how we want to adjust the track and how we used it, the first reaction was, that's not possible. And the reason why it wasn't possible was because it was never before. so we learned to work on these things and try by experience to come up and doing step by step. So we started there and with a track for 300 kilometers per hour, a super elevation of 170 millimeters, and wide parts we did without any bracing. The track was just swimming there, even though we used it. And with measurements, stress measurement, and all these things, temperature, we could show that it's possible. Oh, one thing maybe I also want to mention here, you see the bowling ball at the upper right. Also a discussion if you're working in engineering hours is how quick is the concrete able to bear your structure. And we implemented there this bowling test instead of the nail groove which was before. The bowling test just showed the footprint of the ball, showed how hard the concrete was, if you could already release it and put the weight into the track and release the fastenings to allow the rail then to move to avoid cracks. The next step was in Switzerland. So we had a long tunnel, almost 5 kilometers, and we dared already to go on the track with the weight of 2 tons. And maybe you see here, these are the little adjustment devices from that time, built up on little prefabricated concrete elements where the structure of the slab track was resting on. Next history, so once it was Cologne, Nuremberg, Ingolstadt, also 300 kilometers per hour, and we had to, or we required for the high performance, for the daily output we required some intermediate buffer of 10 cubic meters, and the weight was more than 25 tons, and how to put such a weight on a just elevated track which is supported every 1.3 meter or every 1.9 meter. And the solution is, and this you always have to keep in mind, and most engineers, and that's the reason why it's easy. If you avoid negative forces which lift up the system, your system is stable. As soon if you put one force in between, which is too high, too big, you damage everything you did before. With this solution, we were able, and running on the track, and you see the tent before, that was for protecting from sunshine, and then also afterwards from sunshine and rain, to equilibrate a little bit the forces. With this system we went on, and the quality afterwards was as required and as desired. We also explored, of course, the impact of our solution, of our supporting systems, being or resulting in systematic failures. And you see just from the line, even though if you're not familiar with the graphic, it's very low compared to this line. Then came our, at that time, biggest project for Rhomberg, and we already worked with Sersa together at that time. It was that 36-kilometer long Lötschberg base tunnel. And it was a single tunnel, and up to 25 kilometers we had to supply the concrete in the tunnel. That meant we how to get into the tunnel, how to achieve higher speeds on the just as-built track. And it was a combination of two things. We elevated track up of 2 kilometers and ran with a very slow speed. We ran the transport trains, conventional freight wagons over it with the concrete. And we could arrange with the client a benchmark for the concrete strength, meaning after having yes, it was 10 Newton per square millimeter, we were allowed to use the track for lighter axis, and as soon as it achieved 15 Newton per square millimeter, we could use the conventional freight trains. Sorry, may I take a quick sip? This is now a project we just had been involved as a consultant. We did something similar in Zurich on the tramway. In Zurich on the tramway, they needed the line during the reconstruction to bring the people to the zoo in the city on the weekends, and we could go on the elevated track. Here, they did it all in Madrid. They were in 2005 it was. They were quite brave. Under this perspective, they just put underneath concrete blocks together with some shims and checks to lift up the track, and they ran the metro cars during the days on it before building it at night and reconstructing it at night. Another project was important for us was the 10.6 kilometer Arlberg railway tunnel, having more than 120 years, or built in 1884, so it's 130 years. We had to replace an old ballast, put out the old ballast, bring in the slab track Austria system, and at the same time lowering the track and doing some works at the tunnel to get a wider clearance profile. Here we could develop equipment and machinery to dismantle the track, the old one, and bringing in the new slab track and everything under the live track, passing more than 90 trains per day on the other side. Last but not least, we had a project in Sweden, in Malmö. We were running on the freshly built track. We had a pump line running on it up to 400 meters, and we had to use immediately the fresh poured track and use it for the concrete supply. And then after 16 hours we could go on and using this track and moving like an Egyptian method coming forth, and we had an average of 350 meters per day, which was in a single bore tunnel quite a good one, with one work shift under the Swedish working laws. This brings us now to recent projects. Slab track is just a part of it. I mentioned the Sledgeras project. We developed a system of cantilever to put the tubings in relation to the new track. I mention it because we were allowed there on the Swiss narrow gauge track, Rätische Bahn, to leave a temporary track, slab track, for 1 year. They allowed us to cast in embedded sleepers and leave them for 1 year, and they're just using it that time. And so you have the opportunity and the possibility to renew the tunnel. The second thing now, please don't take out the cross and the garlic. So it's maybe a little bit new, and I would like to explain it. We are unfortunately we didn't build it in at the moment. We have a Russian joint venture partner, so the subsidiary company of the Russian Railways is our joint venture partner. They want to implement the solution for using a track for overnight possessions, to implement it on the Trans-Siberian and BAM line. And of course, like everywhere, they are very cautious. And I don't mention now the bracing. This is now for a very low speed during the daily hours to bridge over this gap. Everything, of course, depends on the length of the gap here and on the speed. But what is the important principle? Important to show. You try to avoid horizontal forces. As we always try to avoid tensions in the track, we avoid the lateral forces by having joints. This is just for protecting. These are steel shims, and this is the conventional system holding the track in place. As said, the braces, it's a different topic. For lower speeds and having always just a gap of a couple of meters, you won't require it. Another possibility to approach it, these are pictures from Ashford-B in UK. We had the chance to implement our system, our EIV system. It's built in this case on the Ashford layer. It's also the question, if you don't have just the overnight possessions, maybe you have a weekend, then you can think of other solutions. Then it's easy to use prefabricated solutions. I'm seeing this here. We developed together with Foslo the BFF 304. The special quality of this system is that you have always a complete underfill. So it's a rectangular. You need a rectangular formwork, which is quite simple, and you can fill in normal cementitious grout. And independent of the super elevation, you always are sure that the base plate is entirely underfilled. I don't know, many people will be familiar with this problem. What happens if it isn't? Last but not least, and I saw some of the people who know that, of course, other thing, and it's a project which wasn't finished. I just would like to mention it out of what's like a consequence of all this history before. Please don't blame me for putting the train on it. We do this in-house, so that's of course no real picture. It should just demonstrate the situation in London Underground to bridge or to have some open gap, a gap where you're able to do works underneath, a gap where you also would be able to improve the soil if something happens. we are convinced that this concept is something which could help to reconstruct track in sensitive areas. And in this case, we used the sleeper, the existing wooden sleepers, having the same principle of the joint here to avoid the momentum, putting shims underneath and just screwing the element in the sleeper. The reason why we believe it also in these solutions, we are able to realign some track, because usually, as I said at the beginning, if you just open 2 meters and don't do anything, you have no chance to do a real realignment and an improvement of the track. And this is just a picture from our test track where we went back and forth at higher speed, lower speed, just to see in the curve with super elevation how it moves and how it does. And my proposal everywhere where I would be, okay, test it somewhere under realistic conditions, do all the measurements you can do in this context to feel safe, put on some safety factors, because we're always talking about loads and the distribution of loads and pressures, pressure and loads which have to be transmitted to the environment. So this, I hope this works. Okay, until it looks like the end and the train is able to pass over, there are a lot of steps necessary. I tried to give a little bit of background of how we are thinking, how we are thinking, how we did approach this topic of slab track construction, and similar to the Austrian railways. And I have to thank, in this context, from the bottom of my heart, sharing experience is something which is very important, and we have the luck that we are able to share from this experience which was made in our country during many years. Oh, what is here? Thank you very much. Otherwise, it wouldn't have been possible to develop this know-how, and yeah, we really do hope that you also take advantage out of this experience we made in the past. Thank you very much.